But today, Wilhelm is here to talk about Lyapunov exponents, Schrödinger cocycles, and Avila's global theory, block Jacobi operators, exploration, and localization. Please.
Thank you, Anders. Thank you for working your way through this complicated title. It's a great pleasure to be here in Britain, in Cambridge. Thank you to the organizers of the spectral meeting at the Isaac Newton Institute. It's a great pleasure to be here. Many years ago, I rented a room in Cambridge from a lady who explained that she was a nurse taking care of this brilliant physicist, and he had this remarkable mind, but she was very concerned about his soul. And I excused myself on the grounds that this is not my area of expertise. This brilliant physicist, of course, turned out to be Stephen Hawking. So it's quite remarkable coincidence. So the talk will have, I think, if I remember, 4 parts. So it's a little dense. I'll try to break this up as much as I can. So on the left-hand side, we have the spectral theory of lattice Schrödinger operators on the lattice Z. I will not touch upon higher dimensional lattices, even though there is tremendous interest in this. But given that we're on the lattice Z, we're dealing essentially with ODEs, actually difference equations, and we can use transfer matrix formalism. And it is precisely this connection with transfer matrix formalism that then allows us to make connection with dynamical systems. So there are crucial notions here. Since we're dealing with ergodic systems, as you will see in a moment, you can associate it with these dynamical systems certain bulk quantities, statistical properties, averages, such as Lyapunov exponents, but also there will be the integrated density of states, which is the limiting distribution of the eigenvalues. That's another average quantity. And crucial to this story is hyperbolicity, which means that in the case of 2x2 unimodular matrices, you will have a splitting of R2 into 2 lines, and these lines are linearly independent and move continuously with the random parameter. But the randomness, and this is kind of the underlying theme of this talk, the randomness will be very limited. We will have finitely many degrees of freedom. In fact, as you will see in a moment, just 1 degree of freedom, a point on the circle. All right. And at some level, I will try to explain all these remarkable islands that are connected by bridges. And so Aubry duality, which rests on the Fourier transform, then allows us to switch between 2 different operators. A key notion in this series, Anderson localization. We will get to that. And Avila introduced this remarkable acceleration, which is the slope of the Lyapunov exponent as you complexify the phase. All right. Can I do this here? So, very nice and simple. The psi n plus 1 plus psi n minus 1 kind of misses the negative 2 psi n, because then it's just a discrete second derivative. This is the discrete Laplacian, but we're not worried about the negative 2 psi n because we include it in Vn. If you're in the periodic case with period Q, then of course you have these, let me try this stick. You have the Floquet matrix where you just propagate from the initial condition to the state at lattice point Q. And then the whole dynamic, so there is one equation that shamefully, do I have chalk? There, thank you so much. So you see should have been on the slide, this equation, which underlies the entire talk. And so to solve this equation, we then, you subtract E from the potential, so you have to propagate this. And since this is a second order difference equation, you start from the initial data, so to speak, psi 1, psi 0. And then to solve this in the periodic case, all you have to understand is the powers of this. Since it's unimodular, the eigenvalues are determined entirely by the trace. The trace is the so-called discriminant. And then you have very well known, you have the modulated plane waves. K of E is called quasi-momentum. And the spectrum famously breaks up into the gaps and bands. What did I do to my chalk? So you have -2 and 2, and here's the energy axis. And then as a function of the energy, you can only do this. So the discriminant can never turn around inside. This is a very basic story. The spectrum consists of projections of these regions. These are the bands in the spectrum. And these are the gaps. That's where the quasi-momentum becomes complex, etc., etc. And the gaps can collapse, which I tried to indicate here, the closed gap. Now, we are not interested, of course, in the periodic case. By the way, in such a setting, periodic, the spectrum is purely absolutely continuous because of these Bloch-Floquet waves. They allow you to write the resolvent. Now, in the quasi-periodic case, or more generally the ergodic case, you have an ergodic dynamical system, you evaluate a function, typically a nice function, continuous or even better, can be a trigonometric polynomial if x is a torus, and t is this ergodic transformation, and you evaluate a nice function along an orbit, and then x is what I mentioned before, that is your degree of freedom, and it can literally just be a number on the circle. And then what happens is, due to the ergodicity, the spectrum, each such hx as a self-adjoint operator, bounded of course, has a compact set, a spectrum. Remarkably, but not difficult to see, the spectrum is actually a compact set, fixed, for almost every x. So there exists a fixed compact set such that this family of operators has this almost surely as spectrum. Moreover, the three spectral types, AC is absolutely continuous, then you have pure point spectrum and singular continuous spectrum. They are defined as what? The complement of all intervals on which the Lebesgue decomposition of the spectral measure vanishes. So I didn't go into great detail about the meaning of this. If this is a bit mysterious what these three spectra are, never mind. So underlying the constancy of the spectrum, or rather the almost sure constancy, is the covariance of the operator. So if S is the right shift, then, or is this the left shift, then the action of that conjugation, which is unitary on Hx, is the same as advancing the dynamics by 1. And this covariance property, since they are unitarily equivalent, yeah, well then the spectra, right? So then you are in the situation where invariant sets either have measure 0 or 1, that's ergodicity. That gives you the constancy. All right. So as indicated to study, so in analogy with the periodic case, we will study these transfer matrices. So we just multiply, but we can't stop at a period. There is no period. Alpha is irrational. And here you see actually this equation written in cocycle form. And so multiplying these unimodular SL2R matrices then allows us to ask about the rate of expansion. So the basic question here is this norm exponentially growing as n tends to infinity? So naturally we take a logarithm, we integrate, and then it is completely elementary to see that this limit must exist. In fact, this limit equals the infimum over n. That's called Feketti's lemma, because these norms are actually subadditive, or rather the logarithms of the norms are subadditive once you integrate, because of this is the Haar measure, right? Lebesgue measure is Haar measure for the irrational rotations. And positive this is always non-negative because the norm of a unimodular matrix is greater or equal 1. So the question is, well, when is the Lyapunov exponent positive? When does it vanish? So another bulk quantity next to the spectra is the integrated density of states, as I indicated a moment ago. So if you restrict your infinite volume Schrödinger, discrete Schrödinger operator to a finite interval 1n with Dirichlet boundary conditions, this means you set the vector psi equal to 0 outside of 1n, Then you have a Hermitian matrix and its eigenvalues. Well, you now look at the statistics of the eigenvalues, the order statistics of the eigenvalues, because of ergodicity and via a trick with traces, just like in any trace identity, they rest on the fact that you can compute traces in two ways, sum of eigenvalues and then sum over the diagonal of the matrix. If you do this, you find that this converges almost everywhere to its average, to its expected value, and that is called N of E, the integrated density of states. You can show that it cannot have atoms. So this distribution function, N of E, cannot jump. It's a continuous function, so it's non-atomic, this measure. And this is the density of states measure, and then a basic question. So if you're in the free case, the potential is 0. Then it's a nice exercise for students to compute the density of states for the free Laplacian. So we're just talking about H0 psi n is psi m plus 1 plus psi n minus 1. Well, this is conjugated to multiplication by 2 cosine theta by the Fourier transform. And then you can compute the integrated density of states. It's an arcsine function. And here it has a Hölder 1/2 type singularity, okay, because for obvious reasons. That's the behavior of the arcsine. So even in the free case, we cannot do better than beta equals 1/2, and that is kind of a wall that you hit. And for a while it was unknown whether in the ergodic case with a general analytic potential on the circle, you have Hölder continuity. This was indeed then addressed years ago by my late and beloved collaborator Michael Goldstein, whom we tragically lost a few years ago. So for the one-dimensional Schrödinger cocycle, this is a famous formula, the Tauler's formula. It's absolutely remarkable, but not difficult to derive. It says that the Lyapunov exponent is the logarithmic potential of the integrated density of states. And if you integrate by parts, you see that L of E is actually the Hilbert transform of the integrated density of states, right? So if you move the D over here, which is a bit formal, but let's not get into that because you can't quite integrate N of E prime over E minus E prime because N of E prime will be 1 from some point on. So apart from, but this is just technical, there's nothing behind it. So you essentially, N is the Hilbert transform of L. And that, of course, since the Hilbert transform is bounded on Hölder spaces, that allows you to transfer regularity properties of L over to the IDS and vice versa. Okay? And this formula does bridge, of course, these two worlds. You have this seemingly completely unrelated question of exponential growth of the norms of the transfer matrices on the one hand, and then properties of the limiting distribution, the order statistics of the eigenvalues on the other hand. And this is one of the magical aspects of this whole theory. Now, in many applications, it is not enough to consider just scalar-valued wave function psi. You actually have to consider vector-valued wave function psi. So one way to visualize this is that the scalar Schrödinger operator is just on the lattice, and then you go on a strip. So you have several copies of the integer lattice Z connected by the natural bonds of Z2. It's a strip, and then you can wrap the strip onto itself. That's periodic boundary conditions, or you just put Dirichlet boundary conditions outside of the strip, okay? That reduces U, but in this, the way I described it just now, B would be an identity matrix, which is good enough for all intents and purposes, but it is not enough in applications. You do have to allow the block-Jacobi form. This happens, for example, in graphene, which is modeled by the spectral properties of graphene, lead to such block-Jacobi operators. V here is a Hermitian matrix depending on your random parameter, and this randomness can be one-dimensional, or it can be a Bernoulli shift, which is the random case, right? So this is exceedingly, if you will, abstract nonsense, the ergodic. This notation just means you evaluate a Hermitian matrix that depends on a parameter, and this parameter lies in some ergodic space. And then dn means you apply dynamics, which could be the Bernoulli shift on the Bernoulli space. That's the IID case, random case. Be it as it may, there is an analog of the Tauless formula that we just saw, but it involves the sum of the top D Lyapunov exponents. What you will see in a moment is this will make better sense once we discuss that actually the transfer matrices are symplectic of such a structure, of such a Hamiltonian. But the symplectic property then implies a symmetry between the Lyapunov exponents. The Lyapunov exponents are essentially the logarithms of the singular values. So in this series, say oscillated multiplicative ergodic theorem, you pass to the polar decomposition, which is just singular value decomposition of these transfer matrices, and then the Lyapunov exponents are indeed the logarithms of the singular values. And if you take a symplectic matrix, it has 2D singular values, but the second block of D are the reciprocals of the first. Okay, you will see this. So then you have D non-negative ones, and they measure the growth of volumes of D-dimensional volumes. So you're forced to do Grassmann algebra, exterior algebra in this setting. It's no longer enough to look at growth of vectors. You have to look at growth of D simplices. Okay, this is Grassmann. And remarkably, this volume growth of D-dimensional simplices is connected to the limiting distribution of eigenvalues, which makes perfect sense because this is still self-adjoint. You only run into serious difficulties if you lose self-adjointment. Okay? And the smallest non-negative Lyapunov exponent, which you find by taking exterior powers of the transfer matrices, plays the role of positivity of L that we had on the previous slide. So it is really the smallest non-negative one that determines dynamical properties. This slide is supposed to indicate physical examples. Here you have two hexagonal lattices stacked onto each other. If you look carefully here, the blue bonds are connected, but here red and blue are connected. It might look a little bit mysterious, but once you have such a structure and the bonds between the different vertices come into play, then you're forced, of course, to look at these block Jacobi matrices. And just for the sake of completeness and honesty, I'm showing here what this kind of looks like. So the bonds, the Hamiltonian will be given by such a 4x4 matrix in the previous two pictures. And this function f of k involves, because of a magnetic field, it involves these complex phases. So I will now move on. This was just to illustrate applications. Another source of these block Jacobi matrices is actually obtained just by taking the Fourier transform of the scalar case. So here you have a scalar Schrödinger operator, and of course this equation is what we're after, understanding the solutions. And now V is a trigonometric polynomial that is real valued for real arguments. So Vk hat will be bar will be V hat index negative k, all right, just because it's real. And then if you pass, but one has to be careful how this really works, to the Fourier transform of this, then this second difference operator will turn into this, 2 cosine. This multiplication operator will turn into a difference operator, right? Because if you Fourier transform this, you get the convolution of V hat with UN hat. So phi you should think of as the Fourier transform of UN, and this is clearly your convolution, right? So Aubry duality, and I'm happy to say more about this in how this really works in the answer period, but for time reasons I want to move on. So there is a way, despite the fact that you have this randomness, or this parameter x, then you have alpha, you can still pass to the Fourier transform, and this makes perfect sense. And then this is now a difference operator of order d, right? Before we had order 1. If this is cosine, then that's a very famous model. That's called the Harper model, and that's self-dual, because then here you will have a Laplacian, you have the cosine, right? So cosine is self-dual. And that's d equals 1. But now we're faced more generally with a difference operator of order 2d. In order to write this in the transfer matrix form, you switch to vectors, not surprisingly, right? Differential equations of order 10 you convert into a first order differential equation for a vector of length 10. And so here is exactly the same. And then you obtain a block-Jacobi matrix just by taking the little phi and sticking it into a column vector of height d, and then you have such a creature, okay? And then that, of course, raises some very interesting questions. If you look at the Lyapunov exponent of this model for fixed energy, how does it relate to the Lyapunov exponents of this model for fixed energy? And here you have many more Lyapunov exponents than here typically, right? So here you just have one non-negative one. Here you have d non-negative ones. How do you relate these? So now, this is about Anderson localization, and let's clarify what this means. So here again, we have the statement of these block-Jacobi matrices, and indeed it helps to set Bn just equal to the identity matrix. V will be a Hermitian matrix. And then the transfer formalism is given by this. So here, of course, you just stack the two on top of each other. So this has length 2d, and this is a 2d by 2d symplectic matrix. Here you have the symplectic property. Okay? That's a reflection of the fact that you're dealing with a Hamiltonian. All right? And again, you have the transfer matrix formalism, and this should clarify some of the slides that preceded this one, because to find the sum of the top j Lyapunov exponents, you simply take the exterior power lambda j. This now is a huge matrix. This has dimensions 2d choose j, because you have to look at all j tuples and make the j vectors with the wedges, right? So you have these simplices, and you look at, for each simplex derived from a basis of the underlying vector space, how does the volume magnify under application of this transfer matrix? And that will give you the sum of the, of course, the sum of the Lyapunov exponents, because in the language of singular values, the simplices will be stretched by the product of the singular values. And you're looking at the top ones, the most stretching that is captured by this, to find the individual Lyapunov exponents, which are the L sub j, which come up in the multiplicative ergodic or oscillated theorem. You have to look at the differences of the sums. And then you have the symplectic property, which relates the first d with the second half. So simply by a minus sign. So it suffices to look at these, and as mentioned before, it is really the smallest non-negative one whose positivity is crucial. And the theorem here that I will try to explain a little bit is that if the lowest Lyapunov exponent is strictly positive and your frequency vector omega that you have on the dynamics. So this is a b-dimensional torus, and you shift by omega, which is a vector of length b. And it had better be incommensurate, so they have Kroneker's theorem, but you need more. You have a quantitative incommensurability condition, that is the Diophantine condition. And if this is positive uniformly for all energies, say, then this block-Jacobi operator exhibits Anderson localization for almost every phase layer. What is Anderson localization? It means the underlying Hilbert space admits a basis, orthonormal basis, of eigenfunctions of this equation. And moreover, these eigenfunctions decay exponentially. Even though I have not so far said much about Anderson localization, this is in striking contrast. Why is this so famous? The whole notion of Anderson localization, it earned him a Nobel Prize. Why is it so famous? Because you should put it in contrast to the periodic case that we just had, on the second slide of the talk. where you have extended states. You have Bloch-Floquet waves, which are just modulated free waves. Yeah, well, they are extended. The spectrum is absolutely continuous. This, in a crystal, this models electric conductivity because the electrons are given by infinitely extended wave functions. This is the exact opposite. This means your crystal is an electric insulator because the wave functions are exponentially localized. You have no transport. All right?
So in this context, when you say Anderson localization, you mean it's only localization. There is no part of the spectrum that's not.
Correct, but this is hidden in the relative energy set. So if this holds for all E in an interval, then you would have Anderson localization on that interval, but you cannot say anything outside of the interval. So I said it in words, but unfortunately the slides did not reflect this, that it's easiest if we just assume this for all E, and then indeed you have complete Anderson localization.
Sorry, what do you mean by Diophantine vector?
Diophantine vector, okay, so it means that your vector will satisfy a condition like this. This is the inner product. This norm is the distance to the nearest integer, and then you need a condition like that for a suitable power A. And this is for all vectors n, not the zero vector. So this is a Diophantine. So you might recognize in this a needed control of small divisors. Indeed, Anderson localization is a long story. Okay? So there's a whole history to this. Beautiful paper, perturbative. So once the potential is large, you put a large number in front of it, then you can hope to do some kind of perturbation off of that potential, that the Laplacian becomes a lower order term. That's, of course, a dangerous game to play. When you do perturbative analysis, you almost divide by zero, small divisor, second order perturbation theory that comes from the resonances. Phil Anderson at Princeton liked to say, and David, maybe you heard him say this, that localization is a game of resonances. Because what it means is that you cannot have an electron that tunnels infinitely through the whole crystal. Right? Infinite tunneling would then mean that you have an extended state. By the way, the construction of extended states is something that we have not really succeeded in doing in the 3D Anderson model. So it's the most famous conjecture of the field. This is the extended states conjecture, that for small disorder you should have in the bulk of the spectrum, not at the edges, the opposite of Anderson localization, delocalization, and AC spectrum. Okay, but how does one approach localization? You really have no choice but to confront, but it is not enough. You have to look at resonance. It's the Green's function. So you look at this here. The P is perhaps a bit confusing. We had before the infinite volume operator, and we restricted to a finite interval 1n. So that was what we wrote, H superscript 1n. Now, we will not look at H superscript 1n. We will periodize this, so sub p, but instead of this, we write pn. So you just wrap the interval onto itself. What that means in the transfer matrix formalism, or rather the d-dimensional version of the whole difference operator written as a cocycle, is that you put ones in the corners, just a one. That's the periodicity. Okay? And then you apply Cramer's rule. And so you have to divide by the determinant. This mu is a rather unwieldy object, which really sets the strip case, or the Bloch-Jacobi case, apart from the scalar case. This unwieldy object is the adjunct matrix. It's a matrix of determinants of minors, of course. So how do you work with something like that? Well, it turns out that, first of all, I will not have much to say about how to bound the numerator from above. The name of the game is that we somehow would like to understand when this Green's function is close to diagonal. So it has exponential off-diagonal decay. This by itself is not enough for localization, but it's a step toward it. And it can only hold for many theta. So there is something called large deviation theorem, which tells you that this Green's function should be good off a very small set of theta that comes somehow from small divisors. And so an important identity, and that's why we switched to the periodic case, is that you can relate the determinant of this object to the determinant of the transfer matrix minus the identity. And now the next few slides get a little bit perhaps more technical. So this is a tool called the avalanche principle. I also like to call it the principle of conservation of eccentricity. And as chair of the department, I had to rely heavily on this principle for 5 years. What it really, there's a picture underlying this principle of conservation of eccentricity. Namely, if you take a unimodular matrix of determinant 1, then it will, of course, turn, so this is an SL2R matrix, it will turn a circle into an ellipse, right? This is just polar decomposition. The length of this semi-axis is the norm of this matrix. And the length of this is the inverse norm of the matrix, okay? And so imagine that you want to break a long matrix product up into shorter pieces. But these are not one-step matrices. There is, say, k steps, and k is large, but this is much larger. And then you hope to understand the long matrix product by iterating small matrix products. But this sounds a little bit strange because, of course, this block can be the inverse of that. You have no magnification. So conservation of eccentricity means that this most expanded direction, as you pass to the next block, should not coincide with the most contracting direction of the next one, because then you lose this. All right? So the expression of this, and I'm following here the notation of Duarte and Klein, who greatly improved upon the original avalanche principle by Michael Goldstein and myself. So what you need is you need a domination for each factor of the largest singular value. So this is dominated splitting, that the second singular value has to be significantly smaller than the first one. That is not enough for your conservation of eccentricity, because you have to make sure that you don't align the image of the most expanding direction with the most contracting direction of the next factor. Rather than trying to align this with the most expanding direction of the next factor, that is not the right way to think. You have to think in terms of not aligning this with the most contracting direction of the next one. And that is what Duarte and Klein call the expansion rift, this. So it's enough to ensure that products are not collapsed. So the way Michael Goldstein and I introduced this avalanche principle is exactly in this form. But we had a different condition that they thankfully removed, is that this ratio actually had to grow with n. And then they saw this and said, we don't like that. It should be enough if that each factor is just large enough, and this singular gap is bounded below by a fixed number. And why does this contain information? Because each of these terms we expect to be of size little n. Well, this error here is also of size little n, but kappa over epsilon squared will be extremely small. And in the applications, Michael Goldstein and I literally used this avalanche principle for 20 plus years. Everything we did is based on that in combination with other tools. For us, this was maybe log n, this entire error, log n. But then you have massive information because you have massive cancellation. Notice in the commutative diagonal case, this is exactly 0. Okay, if the GIs are numbers, then this is identically vanishing. But in the non-commutative case, this has information. And how am I doing on time? I should go for another 20 so minutes. Is that good? 20 minutes. All right, then let me try and just say a few words about how this avalanche principle is used. You are forced in the block-Jacobi case to really think about Grassmann algebra and D-planes. So you have a 2D by 2D symplectic matrix, but essential here is the volume of D simplices. And so you have this Plücker map, which takes the span of D vectors into the wedge, that's the simplex, but with a sign. The wedges are anti-symmetric, okay? And then our GIs in that avalanche principle are, of course, the exterior powers of the individual transfer matrices. And as discussed, we need to worry about the most expanding input. This generalizes this picture, but the input lies here, no? Ri, the most expanding input line, and then you map it over here. So the Li lives here, and the Ri I haven't drawn. It's just a unit vector. It's the eigenvector of Mn star Mn. Okay? And then what you need to do, that's exactly what we discussed before. This output, which is Li, cannot align with the worst enemy of the next input. So that is given by this inner product. And how to control such an inner product? Well, that's kind of the name of the game here. And what's remarkable, if you remember, we worked with the periodic, that's essential, quite surprising, but essential, the periodic boundary conditions here. Because then your denominator, the denominator of the Green's function, which is the determinant of these periodic Hamiltonians, can be written in this form, and then you expand that by this beautiful formula. So determinant of matrix minus identity, you see it immediately if you diagonalize this. Then it's just the characteristic polynomial, so you just expand, you get these traces. And then how do you control such a horrible alternating sum? Well, your only hope is that one term dominates and everything else is an error. And that's indeed true, and it comes from the positivity of this. That ensures you that these traces, exactly one is dominant, namely L equals D. And let me not get into the details of that. I'll be happy to talk more about this later, but let's move on to Avila's remarkable acceleration, and then we'll connect it in part 4 to a zero count that Michael Goldstein and I introduced many years ago. So now we're going to step quite daringly into the complex plane. So instead of the torus, the circle, we will now expand the circle slightly or contract it. So you can, of course, just view the torus as a periodic line identified, and then you look at parallel lines. So you think of cosine x, nice enough, but now you put cosine x plus I epsilon. That, of course, is no longer real, and you lose self-adjointness. All sorts of things happen. But nobody can prevent you from looking at the transfer matrices in that case. Doesn't matter that you're not self-adjoint, you just go on a parallel line. And you repeat the construction of the Lyapunov exponent. Everything works. And then it turns out, because of the Hadamard three-circle theorem, that this Lyapunov exponent, A epsilon is the complexified cocycle, as a function of epsilon, this is convex. That's the Hadamard three-circle theorem for subharmonic functions. This, of course, is analytic. It's very important, otherwise, where's the subharmonicity? It comes from analyticity. What Avila realized, quite remarkably, is that not only is it a convex function, but it's piecewise affine. Okay? And you will see pictures in a moment. And a fundamental theorem is not only is it piecewise affine, but the slopes are integers. Once you hear that, you think of a winding number, right? Integer, where is a topological thing? Where does this discreteness come from? Yeah, that's a remarkable insight. In the uniformly hyperbolic case, which I'm indicating here, when is the cocycle of a Schrödinger operator uniformly hyperbolic? If and only if the energy is not interesting, meaning it is in the resolvent set, okay? That goes also by, this is an ancient result from '86. It comes, Russell Johnson was a student of either Sucker or Cell, so there's something that might have been forgotten today, the Sucker-Cell spectrum, but they also introduced, I think, the exponential dichotomy. That most certainly has not been forgotten, exponential dichotomy. In that community of well, that comes from Sucker-Cell, that's synonymous with, exponential dichotomy is synonymous with uniform hyperbolicity. And, whoops. So if we now look at Schrödinger cocycles with energy E, and remember that we are actually complexifying X, but then we look at the slope at the circle itself. So epsilon equals 0, look at the slope. Then you distinguish these three cases where the Lyapunov exponent is positive, then the slope of the complexification in the phase is also positive. That's supercritical. Lyapunov exponent vanishing, then you have to distinguish slope positive or slope 0. All right, and for the almost Mathieu operator, which is the Harper operator, there's just 2 lambda cosine 2 pi x. If that lambda is less than 1, you're subcritical, critical, and lambda bigger than 1, supercritical. So here come the pictures. This is the Lyapunov exponent, L sub epsilon E. It is even here, not by accident, because you have a real valued potential on the real circle. So they have this symmetry. And these, so it's clearly convex and piecewise affine, and that's the supercritical case. So that's L positive, acceleration positive. And this turns out to be, and this appeared in Avila's ACTA paper from 15, he showed that generically in the potential, there is a notion in dynamical system called prevalence. So, if you vary the potential, you will never see this. Lyapunov exponent 0, but positive slope. But this turns out to be a very interesting case, and Avila formulated a conjecture concerning this and then proved it concerning this picture, that if the Lyapunov exponent vanishes and you have 0 slope, there's a very strong form of vanishing Lyapunov exponent because it does so uniformly in epsilon. That might make you think if the Lyapunov exponent is 0, you have no growth, or at least sub-exponential growth of the norm of the transfer matrices, that you should maybe look like a rotation, because rotations have Lyapunov exponent 0. The question is, can you reduce yourself in some shape or form, like in Floquet theory, which is really reducibility of the cocycle to a rotation? And that's the almost reducibility conjecture, that if this happens, you can almost reduce yourself in the sense of Eliasson. That means that you can't hope to reduce yourself to a constant matrix by an analytic conjugation, but you can do so up to any epsilon uniformly. So in the closure of all conjugations, you will find constant matrices. Okay, so we're back to Aubry duality. What am I trying to say here? You take the scalar case with a trigonometric polynomial, you pass to the Fourier transform, that's the Aubry duality, and then we have this block-Jacobi matrix. So now, what's remarkable, if we want to, here we have one interesting Lyapunov exponent, L, the other one is just negative L, so L. And we would like to understand, suppose you are subcritical here, so that's this picture. In the sense of Avila, we look like this in the scalar case. What does this have to say about the Lyapunov spectrum of this dual? And remarkably, it turns out is that the acceleration counts the number of vanishing Lyapunov exponents of the dual. And this is an observation that, maybe I'll jump here. So this is an observation that appears in the ICM talk of Zhytomyskaya. It's very useful, that the vanishing of the, so kappa E, the acceleration of the scalar operator, counts the number of vanishing Lyapunov exponents of the dual. All right? And therefore, in the subcritical regime, if you have no, if the acceleration is 0, so if you look completely flat and the Lyapunov exponent is 0, then you can't have any vanishing Lyapunov exponents in the dual, which is the block-Jacobi matrix. And therefore, the lowest non-negative one is actually strictly positive. And then you have localization here. And then there is a way to go from localization here to reducibility there. okay? And that's based on the work of Avila, which is, we call the almost paper. The paper is, the title is Almost Localization and Almost Reducibility, okay? So now let me move on. So here that summarizes what I just said. The Haro-Puch formula is a remarkable thing. Let me actually go back to it. I skipped it for time reasons, but we should really maybe talk about this. So as we saw, you dualize, you Fourier transform in some sense, a scalar Schrödinger operator, so this equation, you obtain this strip operator, a block-Jacobi matrix, which has many Lyapunov exponents, many as the degree of the trigonometric polynomial of the scalar operator. And there is a remarkable formula due to Haro and Puch, that's a paper in the journal Nonlinearity from 2013 or 14. And it says that the Lyapunov exponent of the scalar is given by the sum of the non-negative Lyapunov exponents of the dual plus this scalar. That's just a scaling term, okay, that has to be there. And this is absolutely striking because how would you, since you passed from this to its dual by the Fourier transform, that is not a dynamical operation. And the Lyapunov exponents are dynamical entities. So how on earth are you going to connect them? And their insight is that Fourier transform is a unitary operator on a suitable Hilbert space, okay? And therefore these two operators, the scalar on the one hand, the block-Jacobi on the other, have the same integrated density of states because they're unitarily equivalent. And then they use they prove a Thouless formula. For this, they have it's given, and then they prove it for that. Okay? And since they are both equal to the logarithmic potential of the same integrated density of states, they must be equal. And then a highly non-trivial question was, so here they relied on self-adjointness. But now imagine you want to do Avila's acceleration. But then you have to complexify x. You have to do this. You lose self-adjointness, right? So you lose, this completely breaks this argument. Nevertheless, you need something like this because to relate the acceleration of the scalar model to the Lyapunov exponents of the dual model, you have to differentiate this in epsilon, which is this imaginary direction. Yeah, so then you need this, and well, that was addressed in two separate papers. So Ruihan and I, as part of our proof of the almost reducibility conjecture, have such an approach to complexify this Haro-Puch formula and face the non-self-adjointness, which is written here in the title. You have an obstruction that's very serious, and a completely different approach was found by these authors. And I think this story hasn't fully been told yet, so there is much more to discover here. This non-self-adjointness is truly remarkable. And I'm happy to answer more questions about this, but in the last few minutes, let me talk about something quite dear to me, which is what Michael Goldstein and I did many years ago in the early 2000s. We started looking at zeros of the characteristic polynomial, which is this creature, but not zeros in E. Those are the eigenvalues. We looked at zeros in Z, which is the random parameter. That is your phase. And why would you do such a thing? Well, it turns out that the average number of zeros in a thin annulus, so here I'm mixing two languages. You have X, that is this picture, but then you have the exponent of that, which of course wraps you onto a circle, that's Z. So parallel to this picture, you have a picture of a circle, and then concentric circles of very close but not equal radii, okay? That's the small epsilon that sits here. And then we counted the zeros, and it turns out that they grow like 2n kappa. So the acceleration is something that Michael Goldstein and I had already in 2005 in our paper on fine properties, etc. And we didn't realize what we had in our hands. We just bounded this by twice the degree of the trigonometric polynomial. Shame on us. We should have just realized that this is an object worth study by itself, and we failed to do so. And these are pictures that I produced with MATLAB, many years ago. And that got Michael Goldstein and I just hooked on the study of these zeros. And it turns out that this was a truly lucky insight. This was serendipity completely. So these zeros in the complex plane look very evenly distributed, and that's if the energy is on the spectrum, and this is if the energy is off the spectrum. Of course, it has to look like this, because if you're not in the spectrum, the characteristic polynomial shouldn't have real zeros in E, right? Because E is not in the spectrum. So here, this is the unit circle, and the zeros look very evenly distributed, but not quite. There's some outliers here, and here you also see strange outliers. Okay, so you can't hope that you have a perfect uniform distribution. And what is all this game about zeros? Let me get to the punchline. So these zeros look like completely mysterious objects. What do they have to do with dynamics? What do they have to do with the spectral theory? Well, they do, because it turns out that the correct Hölder exponent is essentially 1 over twice the slope of the Lyapunov exponent in the complexification, which is Avila's acceleration. All right, and remember from this picture, which is still here, here you have Hölder 1/2 for the free Laplacian. So if the acceleration is 1, you hit exactly this 1/2. And let me jump to the strip case. There is a notion of zeros for Jacobi matrices, and this is a theorem that we proved a few months ago. It appeared on arXiv in November of 25, that if the lowest non-negative Lyapunov figure is actually strictly positive, then you can find a notion of acceleration, which is not the complexification of this one, but of the sum of the first d non-negative ones. That's always the sum. You look at volume growth of d simplices. And then the Hölder exponent of the integrated density of states is essentially 1 over twice this acceleration in the Bloch-Jacobi case. Okay, and here you will find a summary of the whole story. So you have the scalar Schrödinger cocycle, which is this equation where psi is a real or complex scalar. The duality forces you to consider Bloch-Jacobi cocycles, but we saw they actually come up in physics in these stacked graphene and other models. So that's Fourier transform / Abri duality. Then from here, you go to in the sense of dynamics, to Avila's acceleration. And the zeros of Michael Goldstein and mine allow you to address both localization of integrated density of states. And so there is some form of commutative diagram, forgive the quip. And well, so these are the scalar objects in the strip case system, Bloch-Jacobi case. You don't have just SL2R, you have symplectic matrices. You have volume growth measured by these Lyapunov exponents, or rather the sum of the non-negative Lyapunov exponents. Once you complexify the phase for this, you have a slope. Okay, that we relied heavily on a beautiful paper of Avila, Zhitomskaya, and Sadel, where they understood how to extend Avila's notion of acceleration and his quantization theorem, which is the discreteness of the slope that's integer valued. They understood how to do this for Bloch-Jacobi matrices, and we rely heavily on that. And so here are the key phrases. You have to face the Grassmann dynamics and expanding d-planes, and how these d-planes then talk to each other. The principle of conservation of eccentricity then applies to d-planes rather than just vectors. The periodicity played an important role because it allows you to connect to traces, and you have this explicit control with this alternating sum of traces. The somewhat mysterious zero count is actually a key to controlling the regularity of the order statistics of the eigenvalues, so the integrated density of states. And this is absolutely striking because you're connecting two very far away islands that have nothing to do with each other, right? And here are applications, how this all comes up. On the last slide, you have a few references, and I'll just keep them there, and thank you for your attention. Thank you very much.
Questions?
Can you put one of your first theorems about localization for three vector vectors, multidimensional?
So help me find this. Did it have theorem?
It was right before part two.
It had theorem on top. So tell me when to stop. This?
So is this potential here is something special for general, because similar for general analytic, you might need some elimination of energy.
So for this, I think it's enough to have analyticity, because this is not based on duality.
Okay, so
This doesn't say that the dual of something has localization. This says that an analytic block Jacobi matrix is well behaved.
yeah, but if you apply this to a scalar operator, would it mean that Rubin-Gauss-Stein can be generalized to also differential frequencies, or?
I see your point. Yeah, so what's for almost every theta, you have a point that this is an overstatement. We have to remove. This is almost every omega. My apologies. My apologies. There is, of course, the elimination of double resonances, which forces you to eliminate. So it's just a typo. My apologies. But there is an arithmetic case where, but
Dual case.
yes, there is an arithmetic case that I didn't, for time reasons, didn't talk about. Thank you.
Other questions? Then I have a question. Can you go to the slide just before you show the graphene gradient, that sort of figure something?
The slide
Just before that, when you talked about things break down, the one before. You mentioned here that things break down when you lose self-awareness.
Yeah.
And since you have applications of physics, the question that I have now is that in which cases, or how would you actually get physical phenomena where you lose the self-adjointness?
Okay, that's a delicate question. If I understood it correctly, you're saying how much applies to this in some kind of physical application where you don't have self-adjointness.
Yes.
We do not have an answer to this, but the non-self-adjointness for us is addressed entirely in this case. So once you pass from V to Vx plus I epsilon, you lose self-adjointness, and then there is a way, and I will now show slides that I didn't have time for. This is a key slide. It looks technical, but A index E comma epsilon is the complexification when you do this. This distance is epsilon. And it tells you how to relate the Lyapunov exponents for epsilon to in the model and its dual. All right? And so this is an explicit computation, if you want, and an absolutely key formula that I think appears in Zhytomyskaya's ICM talk, this one here. So look at this. It's epsilon E on the left-hand side is the Lyapunov exponent complexified in X, right? And you have an explicit formula that actually computes it. So this is a delicate thing that only applies to the non-self-adjointness coming from I epsilon. I have no idea how to do this in a general context where you lose non-self-adjointness. This would be model specific, but it's a brilliant question, and this is what I alluded to when I said that much more needs to be understood here. There should be we're missing, there are islands and we have to connect them, and okay, but non-self-adjointness is a hard problem.
The questions then? Well, I think it's lunchtime, so let's